Let's talk about digital identity, the podcast connecting identity and business. I am your host, Oscar Santolaya. Hello, and thanks for joining to this episode of Let's Talk About Digital Identity. And one aspect that is connected to identity and has been like that for many years is face recognition. You have heard a lot in the past years, but also there are new challenges in these recent years. For instance, by the use of face masks, as you can imagine. And for having a deeper conversation about face recognition biometrics, we'll have a special guest today who is May An. May is a scientist at the National Institute of Standards and Technology, NIST. Her research focus includes evaluation of face recognition and tattoo recognition technologies. May has authored and co-authored a number of technical publications, including the accuracy of face recognition with face masks, evaluation of face morphing detection algorithms, demographic effects in face recognition, performance of facial age and gender estimation algorithms, and publication of a seminal open tattoo database for developing tattoo recognition research. And for this, she received the Special Contribution Award at the 2015 IEEE International Conference on Identity, Security, and Behavior Analysis. May was awarded the Department of Commerce Gold Medal Award in 2020 and was a recipient of the 2020 Women in Biometrics Award. Hello, May.
Hello, Oscar. How are you?
Oh, very good. And really pleased to have you and have this conversation with you.
Yeah, I'm quite happy to be here. Thanks for having me.
Fantastic. We definitely want to hear more about yourself and how your life led you to working now at NIST.
Yeah, so I had started my career out of college, actually working for a defense contractor called Lockheed Martin. Mm-hmm. I was hired into their engineering leadership development program. And there I had the opportunity to do rotations across different business units and projects, doing software development and integration work for various government contracts, including running an internal research project, looking at the time, integrating web services with network layer protocols to prioritize certain types of network traffic. I also led a field deployment team where we installed passive radar systems in the field to collect data. But about 7 years with Lockheed, I decided it was time for something different. So I ended up getting a job interview for a guest researcher position, which happened to be with the biometrics group at NIST. And at the time, I didn't have any background in biometrics, but I still ended up getting the job. And that's how I started my journey at NIST.
Oh, excellent. Quite super interesting things before NIST. So we'd like to hear also, now I would like to hear what is specifically the work you do at NIST.
Yeah, so looking back, I've been here at NIST for close to 10 years now, and I've had the opportunity to work on a number of biometrics projects. One of my first roles at NIST involved developing software for a large-scale iris recognition evaluation. Later on, I also ran a tattoo recognition program focused around testing automated tattoo recognition capabilities, and also the development of best practices on how to actually collect tattoo images to support image-based tattoo recognition. But most recently, though, I've been working on projects focused on face recognition, and in particular, running various testing efforts within our face recognition vendor test, or what many people know as FRVT. So NIST has been doing work in the area of face recognition for well over 2 decades now. Mm-hmm. And FRVT has sort of been our flagship face recognition test program. And today it's an ongoing test where developers send their algorithms to NIST and we test them on any number of sequestered data sets that developers presumably have not seen before. And the tests that we run are free and open worldwide. We don't charge anything. Mm-hmm. What it really does is it creates a level playing field because developer software is run on the same data in the same way on the same hardware. And we document results in public reports. And because we publish the results publicly, the research and the commercial community, they pay attention to this. Customers and end users and policymakers also pay attention to our reports. And what we found is that our evaluation process actually helps develop and improve technology over time because the developers are able to use the information that we provide back to them to improve their systems. So, and that's a lot of what we do. We publish reports with numbers and the metrics and protocols that generated those results. And we let the readers really decide what to do with the information. And sometimes as an outcome of our tests, a need for a particular standard is identified. So we go off and we develop those standards. But currently, our FRVT program includes tracks to evaluate core face recognition capability, as well as other activities that will add and modify based on the needs of the community. And a recent example of that is a test we ran evaluating face recognition on people wearing face masks, which was a need driven by COVID-19, where face recognition systems may have to deal with subjects wearing masks.
Yes, of course, very, very topical. And I was about to ask you actually if the work that NIST does is only for American companies or institutions, but you already told me that any developers, any company doing technology, either private or public in any country in the world, can submit their algorithms or their software to your department, to your group.
Yes, as I mentioned, our evaluations are free and open to anyone worldwide. We have a large percentage of the commercial face recognition market who participates in our tests, and we're always open to academic and research entities participating as well.
Okay, sure. Also academic as well. And if we see from the face recognition system that are already commercial, that today people are buying or institutions, companies are using, which one are the most commonly used applications today for face recognition?
So the applications of face recognition really have expanded over the past 10 years. And this has to do with face recognition undergoing a technology revolution really over the past 5 to 7 years. Mm-hmm. And applications can range from unlocking our cell phones every single day or using e-gates to enter or exit countries. We've also encountered some very unique and interesting applications. There was one news article that talked about how face recognition was being used in some parks in China to ration toilet paper and to battle toilet paper theft in public parks. So face recognition is being used in many, many places. And in our tests, the number of face recognition providers out there have grown significantly as well. But one thing I'd like to just sort of mention is that there's a lot of questions about how accurate and the state of the art of face recognition today. And it really depends on the algorithm. There are some algorithms that are quite capable and very accurate, but there's also a long tail of sort of not so accurate algorithms that we've tested before as well. So there are large differences between the good algorithms and the bad ones.
Yes. So let's move the conversation to, you mentioned the face recognition vendor test. That's a test that your group does regularly.
Yes.
Tell us you mentioned already a bit of the effectiveness. Also
Sure.
To clarify, there is a verification and identification. If you can tell us also the difference on that and how it goes with the effectiveness.
Yeah. So we run 2 tracks that involve core accuracy, and we look at the first evaluation is what we call one-to-one verification. So essentially, we're trying to figure out how well the algorithms can take 2 images and determine whether or not they're the same person. Mm-hmm. And as I mentioned before, one-to-one verification applications include, using face recognition to unlock our cell phones or trying to authenticate our passport when we're trying to cross an e-gate, for example. In one-to-many identification, that use case involves a database where, given a database and an image that you want to search against the database, we measure how often the correct mate is retrieved from the database and how often an image of a person that actually doesn't exist in the database actually false positively gets retrieved. So those are the 2 use cases. And so to give you an idea of the state of the art here, on well-controlled photos, so well-controlled full frontal, well-lit images, when doing one-to-one verification, back in 2017, the error rates or the false rejection rates were about 3% for the most accurate algorithms. Fast forward to today, 2021, those error rates have come down to about 0.2%. So, we've seen significant improvements in the state of the art in face recognition. And we've seen that the good algorithms have the ability to see through some of the traditional difficulties in face recognition, such as poor illumination, variable facial expression, and pose. On the one-to-many end, there's evidence that some algorithms can now do profile to frontal matching, meaning being able to use a profile or a side view image of a person and to find them from a database of frontal images. So the top performing algorithms currently in our tests can use a profile image, search it against a database of about 1.6 million people, and find the correct person at rank 1 about 94% of the time. So, I mean, the technology really has come a long ways, especially when you only have half of the face available to you to do recognition with. But with that said, though, there still remain certain limitations to the technology, such as being able to differentiate between identical twins, demographic differentials, and extremely poor quality photos as well. And we've seen that image quality can range from, excellent, good, bad, ugly, and lots far beyond. Also, as face recognition technology is progressing, at the same time, though, ways to exploit the vulnerabilities of face recognition has been advancing as well. And examples include face morphing and presentation attacks. And these types of topics impede on the security of your system. So this is something that developers and end users need to pay attention to.
Yes, but as you said, in the best cases, in the best algorithms, the results are quite impressive. I would say it's really very accurate. That's great. Tell us now about these aspects of face recognition that you are investigated. For instance, you mentioned briefly about the demographic effects. If we start, for instance, with the effects of face masks.
Sure. So we conducted a study looking at face recognition accuracy on people wearing face masks. And this was motivated by the pandemic that we're in right now, which has brought on the global practice of people wearing protective face masks in public places for safety purposes. So there's a need to be able to use face recognition on people wearing masks. As I mentioned, from trying to unlock our cell phones while we're out grocery shopping to when we're wearing a mask to cross gates at airports without needing to remove our masks. And the presence of masks, it presents a problem for face recognition because regions of the face are occluded by masks, including the mouth and the nose, which contains information useful for recognition. So what we did in our study was we applied solid colored masks digitally to a large set of photos, millions of them, and then compared the accuracy of face recognition algorithms on both unmasked versus masked images. And we also looked at how changing the shape of the mask, the color of the mask, and the amount of nose coverage of the mask would affect performance. So initially, we had tested algorithms that were developed prior to the pandemic. And what we found was that accuracy with masked faces declined substantially across the board. And the majority of the pre-pandemic algorithms just didn't work with face masks, and the error rates were very high. Subsequently, though, we started receiving algorithms developed after the pandemic was declared, and it's clear that some developers have started adapting their algorithms to better handle face masks. So currently, in the best cases, the error rates on masked faces are anywhere between 2 to 5%, which is comparable to where face recognition technology was about 2017-2018 timeframe on unmasked photos. But if you think about it, right, these results are still quite impressive given 60 to 70% of the face is covered by a mask. So the presence of face masks has set the technology back a few years, but the technology may still be usable depending on your application, right? And we found that the amount of nose coverage had an impact on error rates. So high masks that covered more of the nose produced more errors when compared to masks that covered less of the nose. We also saw that the shape of the mask mattered. There were higher error rates in the wide masks when compared to round masks. And this makes a lot of sense because the wide masks tend to cover more of the face than the round masks do. So the study that we ran was a laboratory test using synthetic masks. And what it does is it gives us a first order answer on the question about whether the existence of face mask occlusions has an impact on face recognition algorithms when compared to people who aren't wearing masks. We didn't use real masks in our data because we didn't have a large data set of real masked images available to us. So the test might be missing certain realities with real masks that might impact accuracy, such as certain textures or patterns that might impact results or the fit of real masks over different faces. And our test didn't take into consideration any interactions with the camera that the mask might have, because many cameras today run with exposure control. And it's possible that a dark mask on lighter skin or white mask on darker skin could cause over or underexposure problems. So I think the best thing for owners and end users of face recognition systems to do is to know their algorithm and how their system performs in their own environment, their own operational environment, ideally using the operational data coming from their systems of people wearing real face masks.
So you have on your group people who are like the testers who, let's say, wear the mask and you test the algorithms?
Yeah, what we did was, for us, we had an existing repository of many, many images. And yeah, we overlaid synthetic masks using software, and then we ran the evaluation. But I think the best thing to assess sort of your system accuracy installed in your environment is to use the data that is collected on your system of people wearing real face masks that are coming through your system. And that will give you a much better answer to how well your system works.
Mm-hmm. And are there many of these, the developers, the institutions, companies that are developing face recognition, many already have adapted their algorithms for the face recognition, for the face masks?
Yeah, so I would say that some of the top performing algorithms have started adapting their algorithms for face masks, but there still exists a number of developers who have submitted algorithms who just aren't addressing the face mask issue. And we can't necessarily compel or control the algorithms that they submit to us. So we just test it and then we report the results.
Sure. Tell us about the face morphing, the cases face morphing.
Yeah. So as I mentioned, right, as the performance and deployment of face recognition technology has started ramping up in the past few years, there's also been an increasing number of technologies aimed to defeat or exploit vulnerabilities in face recognition systems. And one such vulnerability is face morphing. And face morphing is an image manipulation technique where you merge the faces of different people to form a single photo. And morphing itself as a concept isn't anything new, and it's really quite easy to do. There are a number of free applications out there that can take two photos and create a morph. But the application of face morphing can actually be used to create a security vulnerability to exploit modern face recognition systems. Because what happens is when you morph, say, two faces of different people, you get an image that looks like both people. Mm-hmm. And if that morphed image gets onto an identity credential, it can be used by both people. Right. Because one, the morph looks visually like both subjects, but more importantly, modern face recognition algorithms are fooled by this morph and will actually match images of both subjects to the morph photo. So imagine if an attacker is working with an accomplice to use a self-submitted morph photo to apply or renew a passport, say. And visually, the morph looks like the person applying for the passport, so it'll likely pass any sort of visual check by an officer. And once that morph photo gets onto the passport, we now have a fraudulent yet genuine document that can be used by both people. And when the attacker takes that passport to try and enter or exit the country using an e-gate, which is powered by face recognition underneath the hood, the face recognition algorithm will most likely authenticate the user with the morph, and that e-gate door is going to pop open. So morphing poses a threat to entities that accept any sort of user-submitted photo for identity credentials. And all of the capable face recognition algorithms that we've tested are vulnerable to this morphing phenomenon. A few years ago, a real case of the morphing threat actually made news headlines. There was a member of a German activist group who applied for a German passport with a morphed image. They morphed a photo of themselves with an Italian politician, and they successfully got the passport with the morph photo on it. And this made news headlines internationally and was essentially a wake-up call for a number of governments worldwide that accept user-submitted passport application photos, for example. So given the security concerns around morphing, NIST launched a program called FRVT Morph. And the goal here was to look at whether morphed images could be detected using software algorithms and how well they work. And we've tested a number of morph detection algorithms over the course of about 2 years. And we've tested them over multiple data sets of escalating difficulty. So our test ranges from using rudimentary morphs that have very clearly visible morphing artifacts to using quite sophisticated morphs where it's really hard to spot any sort of image manipulation. And it really is it's the sophisticated morphs that are concerning because that's what an attacker would realistically use if they were going to do this. As of today, automated morph detection still remains a really challenging problem. Morph detection using a single image in isolation is a very hard problem, and we really haven't seen any breakthroughs in terms of technology in that aspect. There is a second scenario where, in addition to the image that's in question, the system also has access to a photo of one of the subjects that went into the morph. And with this additional bit of information, we have seen some promising results in morph detection capability. But with that said, there's still quite a bit of progress to be made before the technology is mature enough for operational use. Other research organizations have studied human performance on detecting morphs, and the consensus is that for morphs that are sophisticated, where there are little to no visible artifacts available for the people to pick off, humans have a very hard time detecting whether an image is a morph or not as well. So given both humans and machines aren't currently reliable when it comes to detecting morphs, it really solidifies the case for better processes and procedures to try and mitigate this vulnerability by preventing morphs from getting into your system in the first place. So putting better enrollment processes in place, whether it's through live enrollment or trusted capture of some form, to ensure image manipulation isn't possible in your process.
Yeah, it's quite a big challenge. I can see, not easy to mitigate. But as you said, the enrollment is very important. So at the time the user is registering into the system, is the identity is the photo is taken by the system. So. And then you say once this photo, the morph photo is on the system, the only way is to find an algorithm to search on the database which of these photos are morphed.
Yeah, so once a morph photo gets into your system, it's really hard to figure out whether or not you have a morph or not. There is one sort of process. If you have a centralized database, for example, the Dutch Vehicle Authority actually ran a pilot a couple years ago where they took their operational driver's license and they created some morphs using people who were in their system, and they did a search of morph photos. And what happened was, given a morph is of, let's say, two different people, if both subjects exist in that database, then when you do a search of the morph against the database, both of those subjects will be retrieved at high ranks with high scores. So something I guess system owners could do is essentially do a one-to-many deduplication search on any sort of self-submitted application photo into their system and start looking for suspiciously high-scoring multiple subjects that come back. And that could be a way to sort of trigger whether or not there's further investigation that needs to happen with the application photo, for example.
What about the demographic effects in the facial biometrics?
Yeah. Demographics is a bit of a hot topic. So the buzz around, I guess, bias in face recognition really started a couple of years ago. There was a study published by MIT called Gender Shades, which tested various cloud-based gender classification algorithms and reported that gender was often misidentified in darker-skinned females. Now, gender classification has to do with facial analysis of a single image, and you're trying to answer, is the person male or female? While face recognition has to do with extraction and comparison of identity information between two photos. So these two are separate things. The reporting of gender classification algorithms being biased got conflated with face recognition being biased, which resulted in often incomplete reporting in the press of face recognition being biased. There was also an influential report that was published by Georgetown University on potential demographic biases in face recognition. They published a report called The Perpetual Lineup, which criticized unregulated police use of face recognition in the United States and talked about the possibility of racial bias or demographic bias, which would impinge on people's civil liberties. So in response to these series of events, one of our partner government agencies asked us to look at this demographic bias problem and to see to what extent that it's real. So in late 2019, NIST published a report on demographic differentials, talking about the various stages of a face recognition system pipeline where bias can potentially occur in the pipeline. And we reported accuracy on over 180 face recognition algorithms across demographic groups defined by sex, age, race, country of birth. And what we found was that there was a wide range of performance among the algorithms tested. So the algorithm matters, and more accurate algorithms are going to give you better outcomes if they're used, obviously. We found that there were much larger demographic differentials in false positive rates when compared to false negative rates. So a false negative, for example, is that when you try to use your face to unlock your phone and you get rejected and you get locked out. A false positive is when someone else is able to unlock your phone with their face. Right. So we tested one-to-one verification algorithms and we tested one-to-many identification algorithms. And for the class of one-to-one verification algorithms that we tested, we found that false positive rates were higher in people from East-West Africa and East Asia than people from Eastern Europe. False positives in females were generally higher than males, and false positives were largest in the oldest and youngest age groups. Now, the magnitude of these demographic differentials differed between algorithms. Most of the very accurate algorithms showed lower demographic differentials. Additionally, some of the outcomes for the one-to-many identification algorithms that we tested didn't show the same kind of demographic differentials as seen in the one-to-one algorithms. There were a handful of developers with one-to-many algorithms that had stable false positive rates across the different demographic groups that we tested. When we published this report, we didn't analyze cause and effect. We put these numbers out, and operators and users of face recognition, need to think about what these numbers actually really means to their operations, right? Because the impact of differentials could vary drastically with your application and associated risks. For example, if you're using a face recognition system to authenticate members for gym access, right? Trying to access a gym, the consequences of a false positive might be, someone getting in and using your gym equipment for free when they didn't pay for membership. Okay. But a false positive in the context of a law enforcement investigation could have much greater consequences. So application matters, definitely. At the end of the report is a list of recommendations for research towards mitigating demographic differentials. And face recognition developers have been actively working on this demographics issue. And NIST plans on putting out an update to the demographics report later this year. And we'll also publish and maintain a leaderboard that will report several numeric measurements of demographic differentials for algorithms as a way to sort of track progress in this area.
Mm-hmm. Yes, the demographic bias, something that has been already in the media, social media in the last months, last 2 years, as you said. And you said from your report that you didn't get what are the causes. You cannot say, for instance, why these developers, this company, had such a poor performance in demographics, right? But is there any pattern you can say now? Or so it's not about trying to blame, but what went wrong in the way they design, or what is a pattern?
So these algorithms were submitted to us as black box algorithms. So we have no idea how they were developed and what data they were trained on. But there was one data point that we found in our study is that many algorithms developed in China did not give the elevated false positive rates on Chinese faces that algorithms developed elsewhere in the world do. So that data point points and provides some, shed some light on the fact that training data matters. So in terms of, recommendation, we recommended that developers try and look at using more diverse training data to support the development of their algorithms.
Yeah, so the training data has to be the widest possible. So that's at least one of the main reasons why most of these algorithms perform so badly on this.
Yeah, I mean, if you really want to make face recognition better, you also want more signals, right? You want more discriminative power from the biometric that you're sensing. So one other recommendation we make is, in addition to capturing face, potentially using iris recognition as well, because there are a number of cameras on the market today that simultaneously capture both face and 2 iris images. So if you could use both modalities, you'll likely be in better shape in terms of accuracy, because iris doesn't appear to have the type of issues that we see with face when it comes to discrimination.
So you mean that at the time that developers create the algorithm, or is for the application that they should use both?
Yeah, it's for the application.
For the applications, right. Yeah, to make it stronger. Correct. And there is one, you mentioned the forgotten demographic, the twins. Tell us a bit about that.
Yeah, twins are what we often consider the forgotten demographic, because whenever anyone brings up demographics, the focus sort of naturally leans towards race or sex or age, right? But twins can exist in any given race, sex, or age group. And about 3% of babies born in the United States are of twins or multiple births. Identical twins are always of the same sex, and fraternal twins can be of the same or different sex. And currently, one of the issues with face recognition accuracy when you get to very, very large population sizes is the presence of twins. Specifically identical twins, because face recognition has issues differentiating between identical twins. So given a pair of identical twins, twin A will authenticate as twin B, and then vice versa, making twins a demographic with a very high false positive rate. So twins is still a bit of an open limitation for face recognition at the moment. And actually later this year, we plan on publishing a report quantifying current face recognition performance on twins.
Yes, very, very interesting. But now that we are been discussing, of course, a lot the perspective of the developer, the company, the technology vendors, technology providers who create these algorithms and the solutions. So what about from the organizations who are going to buy some of these solutions, such as law enforcement, government, can be another company that needs this authentication? And what can someone who is evaluating one of these products should check? What will be the top on your mind?
Yeah, again, depending on what you're using the face recognition system for, accuracy is one thing, right? But outside of accuracy, there are a number of other things that organizations probably should pay attention to. For example, for complete systems, you might be interested in how quickly the face recognition system works, how mature the software is, how reliable it is, how easy it is to integrate into your environment, the costs, support for human review. And all of this can vary widely between technology providers. But I would recommend that anyone who's looking at procuring a face recognition system definitely do some research into how well the technology works and what types of limitations, I guess, the developers themselves have found, and also from other third-party independent test organizations have found as well.
Mm-hmm. And it's very likely that for the best providers, it's possible to find on your reports.
Yeah, as a part of FRVT, we actually have and maintain a leaderboard for both the one-to-one and one-to-many test cases. So those leaderboards are public and they're updated on sort of a bi-weekly or monthly basis whenever we put out new results. So, interested parties can go to our website and take a look at that information as well.
Well, excellent to know. That's super valuable, I believe. But thanks a lot for this conversation. But I'll ask you a final question, May, is for all business leaders that are listening to this conversation now. So what is the one actionable idea that they should write on their agendas today?
Something that I've learned since working in the field of biometrics is that nothing is permanent except change. And maintaining sharp awareness and staying educated, really, and adapting to the ever-changing state of everything around us is extremely important. This pandemic is a perfect example of how quickly changes to technology requirements can occur. Almost overnight, right? From the need to process people wearing face masks to finding new ways to implement contactless biometrics. And at NIST, we're constantly learning new things about this new generation of algorithms and trying to adapt our tests to keep providing relevant information to the community. But not only does change awareness apply from a business and technology standpoint, it also applies to people. And this includes understanding and adapting to the changing needs and state of mind of your employees, your coworkers, and your family. The needs of my children have changed during this time that we've had to quarantine at home, with them not being able to see their friends and their schooling shifting to a completely virtual environment. So the type of support that they need from me has changed. And perhaps the type of support that I need from them has changed as well. And I imagine things will continue to change as we hopefully navigate through a path back to what we know as normalcy.
Yes, yeah, completely right. Being ready to adapting to changes. Yeah, it's true. I think no solution is going to solve the problems forever. So it's going to be ready for hearing the signals, what are changes coming.
That's right.
Again, thanks a lot, May, for this fascinating interview with you. And please tell us, if people want to learn more about the work you are doing at NIST, what are the best way to find information or get in touch with you?
So all of our projects are public, and the reports and what we did and our tests and our activities are available online. So if you go and you Google NIST FRVT, that will take you to our FRVT web pages where you can find out more information about our face recognition tests.
Okay, perfect. Thanks a lot, May, and all the best.
Thank you so much, Oscar. It was great talking to you.
Thanks for listening to this episode of Let's Talk About Digital Identity, produced by UbiSecure. Stay up to date with episodes at ubisecure.com/podcast or join us on Twitter at ubisecure and use the hashtag LTADI. Until next time,